We'd already gotten rid of a lot of things that we knew weren't going to cause it to fail. But those details took us forever. Wasn't sure I was ever going to get through it. It was that complicated. So the essential findings were: fire did not cause the collapse of WTC-7. Point number one. I told you that on September the 6th, 2017. 2 years later, I'm telling you the same thing. Temperature was not high enough to cause weakening of the steel framing. However, further, that thermal expansion did not result in a loss of support for the beams and girders, yet NIST claimed otherwise. So here's an important point. Here's a point. I'm already different than they because of that issue right there. The beams are saying in the floor system expanded and caused a problem. I'm saying it expanded but didn't cause a problem. And I'll share the details here shortly. WTC-7 did not experience a progressive collapse as claimed by NIST and others. It was actually a global collapse. So those are my essential findings that are really critical to what we're doing. This is kind of what I'm going to share with you before I even tell you the story. The left is our UAF collapse simulation of this building, which is on our right, which is a video collapse. So I want you to watch this and watch that and assess it yourself as to what you believe might be something to think about. Okay, here we go. Okay, that's our simulation. And I'll give you a number of details as we go through it. The problem is this. History, the National Institute of Standards and Technology, NIST, reported that WTC-7 collapsed due to fire at 5:20 in the afternoon on September 11, 2001. And NIST also reported no other tall steel frame building had ever failed due to fire. So, why is that so important? It's important because it's essential for ensuring the public safety that a failure mechanism for a structure is important to be understood so we can prevent it from ever happening again. We can't afford that. So, therefore, architects and engineers, 2,600 of them, 2,600 architects and engineers who put together a non-for-profit group, funded this university to re-examine that WTC-7 collapse. And the money came from them through their own donations. So this is how that worked, okay? Now, the key findings of this UAF research team, I'm going to give you a little more detail. So now I'm getting into the details, okay? And I apologize if I'm getting too detailed. So please drag along with me. The approach one is that NIST overestimated the exterior wall rigidity. Subsequently, NIST argued floor expansion was westward as it moved from the east exterior wall. So remember that east is to your right. East is to your right, okay, as you're looking at that complex, at that building. And imagine that they locked that wall system and then heated it up. What's going to happen? It's going to move away from it. No, that isn't what happened. The building couldn't do that. It would have to move away from the stiffest area, centroid, what I call the point of zero movement thermally. And that was very close to the elevator shafts. Okay? So actually, the exterior walls were flexible and thermal movements were from the point of zero movement near the elevators, and therefore planar thermal movements were from west to east at column 79, not the other way around. When I presented that in Boston and in New York at the time, New York was at the 15th anniversary, Boston was a little bit later, that was the first time they'd ever heard such a thing. About this. I mean, everybody had been always assuming that the movement was exactly what had been stated it was. So NIST argued that girder A2001 moved off the bearing seat, and I realize I don't have a picture here, but we will get a picture here shortly of this. Moved off the bearing seat at column 79. UAF found that that movement at that seat was in the opposite direction and was very, very small and not an issue. The UAF findings showed also that the relative movement of A2001 to the base plate on column 79 was actually 3.68 inches for a non-composite movement. Non-composite means that the concrete and steel move separately with respect to one another. They're not being pulled together. 2.18 inches for partially composite. That's when I had friction working and the concrete was sitting on the steel and we could have that. I'm not saying that's what was there. I'm saying I'm looking at the extremes. Looking at composite versus non-composite. So for non-composite, it was 3.68, partially composite 2.18, and less than 1 inch for composite behavior. The condition at the time of the fire was composite, by the way. Okay, this is column 79. This is the thing I'm talking about. And in here, we ended up with overall movements that you see over here and we're moving from column 79 to the east. Over here is about where the point of zero movement is, and there everything's moving from west to east. Okay? Are you following this? And this is on floor 13. Are we all okay? Feeling good about it? All right, good. So approach one, NIST, wait a minute, I'm sorry. So the other thing I want to share with you is the movement of girder A2001 relative to column 79, floor 13 was as follows. We looked at composite, partially composite, non-composite, and NIST only looked at one thing. That was 5.5 inches to the left, non-compositely, and these are the things I just told you about a few minutes ago. NIST later revised their girder movement 6.25 inches after being alerted that the bearing seat was 12 inches wide and not 11, as originally stated. And NIST also only examined the non-composite condition, which wasn't the case on that day. It was truly composite. Approach two. We took Abacus, very, very sophisticated finite element program, which if it doesn't have the algorithms you need, you can add them to it. It's really quite powerful. It's really a wonderful program. We looked at that program and we used it to simulate, using solid elements, the floor framing for floor 13. That's where all the buzz is about, floor 13. These elements were used to evaluate the validity of NIST's collapse initiation hypothesis, and the NIST assumptions were the exterior east wall was fixed, and that was not a valid, it was not valid, it was flexible. I think I've already told you this more than once. Shear connectors on several beams were broken. We saw no evidence to consider this to be a valid assumption. NIST assumed no shear studs were on girder A2001, but yet we found that there were shear studs on that girder based upon the legal records, the court records. NIST assumed bolts fastening girder A2001 to its seats at column 44 and 91 were broken. This was also an invalid assumption. Okay, so here's what we did. Using the NIST assumptions, even though we know that they're not right, if we use those girder assumptions, and if girder A2001 was going to be heated up, we would find it would get trapped behind the west side plates on the flange of column 79 and wouldn't be able to get off of that seat anyway. We considered a movement to the west to be invalid because the east exterior wall was considered fixed. This was not an invalid assumption. And furthermore, the column flanges had those side plates that would prevented the girder from walking off the seat. All right. Approach 3. We also used SAP 2000 to three-dimensionally simulate numerous failure hypotheses. What I'm saying here is in each case we examined failure modes and evaluated if they would lead to the total collapse observed on September 11th. So we tried this and we tried that. Well, there was a lot of different opinions about what happened there. So we tried to consider every possible situation to see if the structure would respond that way. Based upon our analysis, we found the following. Columns 79, 80, and 81 did not fail at the lower floors of the building as asserted by NIST. if columns 79, 80, and 81 would lead to failure of the next row of core columns, exterior columns at the southeast side would be overloaded and the building would tip. That means, if that was true, that means that the building wouldn't come straight down, as you've already seen. It would have tipped. Couldn't have been that. Simultaneous failure of all core columns over 8 stories, followed at 1.3 seconds later by the simultaneous failure of all exterior columns over 8 stories, and those produces almost exactly the same behavior that you saw in our video. So think about this: entire floor, all the interior core columns came out simultaneously. The exterior 1.3 seconds then came out, and the building then dropped in free fall. Actually, the penthouse came down 5.5 seconds earlier. So, and I'll show you all those details. Based upon simulations, the collapse of WTC-7 was a global failure involving near simultaneous failure of all columns in the building and not a progressive collapse involving sequential failure of columns throughout the building that lots of people have argued were. The details behind the science. In the following slides, I'm going to attempt to go through the details of our study, and I apologize if I'm going to bore you to death. First, we determined mechanical and thermal centroids at floor 12 and 13. That's the first thing I did the first day we started, because I felt like, number one, we needed to know if you heat up a floor, where it's going to be moving with respect to. Okay, so I've said this more than once. But we also wanted to know the mechanical centroid, because if you apply a load somewhere on the building, is it going to twist? Is it going to rotate? Is it going to tip? What is it going to do? We need to know its response. It's like a human being. You do something you're going to get a response. So a building behaves similar. Sometimes it doesn't like you. So second, we developed a nonlinear spring stiffness for the connections. That was to save time and also to get an understanding of how the connections between the girders, the beams to the girders, and the girders to the columns actually behaved. Then we developed equivalent nonlinear spring for the computer model. Third, the concrete floor was built using stay-in-place steel forms, which means the stiffness of the floor was different in mutually different directions. The forms actually have flukes. They actually are stiffer in one direction than they are the other. It gets poured full of concrete, and therefore the structure behaves differently. So this was accounted for by developing equivalent performing elements that we did to save time. Then we could take those equivalent elements, basically we're substructuring the structure and looking at its behavior. And fourth, we examined the planar thermal movements of the floor for composite behavior. That's when all shear studs were in place. Partially composite, that's for frictional resistance between the concrete floor and the steel framing. And then the non-composite, in which we allowed for no shear studs or frictional resistance. Okay, which is the way NIST did. This is a look at floor 13. And if you look at this picture right here, there's column 79. This is the exterior wall. So at the exterior wall, the amount of movement is 6.844 inches to the right in the X direction. At column 79, it's about 5.801 inches. So basically, about an inch more right here. So where is all the movement coming from? So look down in here. +5, -4. Somewhere in this zone is where that movement is occurring from. You see what I'm saying? So this was a computer model of the heat that was put on that using the NIST fires, and then we simulated them to see if we agreed with them. This is column 79, and at that floor 13, we had 1.85 inches to east and 0.94 inches north of how much that moved at 600 degrees C. Evaluation of the NIST hypotheses is what we're going to talk about next. Here is column 79. Here is column 80, 81, column 44. Here's a group of beams up here with horizontal stiffeners between so that they wouldn't buckle. And here's the other beams, B3004A, and so forth. The reason that's kind of important is we're going to take a computer model and virtually simulate that and then use the NIST assumptions to see if they were actually correct. I didn't want to say, okay, I'm not going to accept it. We needed to be able to be sure that we knew that whether it could have been correct or not. All right, so taking that, NIST argues that the absence of girder shear studs caused the girder to not have sufficient lateral restraint. Failure of the girder to column connections were caused primarily by thermal expansion of large span lengths of the northeast floor beams. This is their arguments. These are not my arguments, please understand that. You see the big letters NIST? Okay, that's not mine. Absence of girder shear studs. If they're absent and it's heating up from, and it's moving from that exterior wall that they claim was fixed, then it's going to go west, okay? And this is plan view, and this is the girder A2001 from the drawings. From the actual drawings, okay? This is just another view, counter-argument to girder missing shear studs. It was found that the court records show that there were 30 shear studs were equally spaced along that girder. So, the solutions that they had based on no shear studs was not valid. NIST conclusions also stated that fire-induced weakening of critical columns did not cause the WTC-7 to collapse, and I don't disagree with that. Temperature in column 79 was below 200 C. That's okay. We got similar. Horizontal beam movements were caused by thermal expansion, no problem with that. And lateral displacement of girder framing into column 79 was a result of thermal expansion of the beams framing into the girder. Basically, they said at column 79 they lost lateral support over 9 stories, which then caused a cascade of failures to occur, and then from that you would have ended up with the failure you would have seen in the video. Keep in mind, if I was to go back, and where's column 79? It's not in the middle of the building. It's over there on the northeast corner, pretty much, right? And notice, there's nothing symmetrical about this building. It's a trapezoid. So those things aren't helping anybody. And it was quite a complex building. The other thing that happened, which we discovered pretty quickly, is NIST modeled the connections within this zone, all around column 79, all that area. But they did not model the connections over here. And they did not model the connections along the exterior. So area 4, where connections were modeled from floors 8 to 14, were in that zone, which really bothered me. Bothered me because it's not representation of what the building had. So outside the selected area, connection failures were not modeled by NIST. This is just a summary of what I just told you. And NIST used fixed or pin. Connections were not modeled by NIST on any exterior walls. And so here we are. So a girder was considered to have lost support when its web was no longer supported by the bearing seat. The bearing seat at column 79 was 11 inches wide. Thus, when the girder at column 79 had been pushed laterally at least 5.5 inches, it was no longer supported by the bearing seat. Really? Well, they changed that from 5.5 to 6.25 later. Right? So NIST results were, okay, so let's just take a look. We're going to take a look at their model, their simulation based on what I've shared with you so far, and the actual footage. So bear with me. Note, in the NIST, no connections were modeled along the outside frame. Just remember that. So here is the simulation that they have. So, that's their modeling. This is again, looking at this side right here, you see that there's an outside selected area that were not modeled, and then this progressive cracks appear to be in 2 different parts. Okay? So here you can actually start to see it, what I'm talking about. You're going to see something going on here. All right? So let's see what it looks like, what I'm talking about. So notice you have different stiffnesses just because of the connection issue. All right? looking at the other side.
So this is the NIST simulation.
So this is the NIST simulation. All right? So what about us? What about the UAF analysis of the NIST collapse initiation hypothesis and the propagation claims? A solid finite element model of structural members in the northeast corner of the 13th floor of WTC-7 was generated. We used Abaqus to do that, by the way, and we used solid elements. A finite element analysis was then performed to replicate the results claimed in the NIST WTC-7 report that girder A2001 was pushed or rocked off its seats in column 44 and 79 to initiate the collapse of the building. Here we are with respect to that plan view for column 13. Okay, we are floor 13. There's column 79 here. Here's columns 80 and 44. We need to focus right here. Girder A2001 spanning from A44, column 44 to 79. Column 79 is circled because that's where all of the buzz was about. This is the virtual model of the floor system from Abaqus, kind of showing you exactly, and you'll see right in here there are frames, because that's another point of controversy. They're claiming those didn't exist. We found that they did. This is the picture of the frame itself out of Abaqus before we perform an analysis on it, before we heat it up. This is the so-called side plates I was telling you about. Here is a W shape, if you look at it. And then there are side plates that extend beyond the flanges, 2-inch by 26-inch build-up side plates, and that's a W14 by 30 structural shape. And so if you imagine that that column had a bearing seat, we'll say, and a beam was up against it, those side plates would stop it from moving off the base plate. And this is what it looked like off the drawings. So this is a plan view connection to girder column 79. And this is girder A2001, by the way. Okay? And right underneath here is the base plate. Okay? This is a view of what happened when we heated it. You can begin to see that this girder tried to shove west using their assumptions, fixed on the exterior wall, all that kind of stuff, and tried to shove, but it couldn't come off of it. So the Abaqus analysis of floor 13 with the assumed temperature distribution from NIST and original load condition, the side plate on the flange of column 79 would have prevented A2001 from moving to the west more than 3.5 inches. Locked in, couldn't do it. So thereby preventing A2001 from losing its support at the bearing seat. Okay, hopefully that's a visual that you can imagine. Okay? Looking at underneath, looking at the concrete deck on top of the beams, this is column 79. This is the girder, column 44, which is on the top part, the north side of that building, exterior wall. Now we're looking at on top of that. So this is without the concrete beams. This is W, column 79, 79, 44. There's W33 by 130 is A2001, and there's your exterior columns. This is a NIST analysis. We ended up with the exterior columns having the buckling conditions, W24 by 55 floor beams. This is W33 by 130. So this is exterior columns, and these are the floor beams that actually were buckling between them. Another view of that. Here's what I'm talking about earlier. I said this beam buckled, that's beam buckled, this is plan view, this is column 79 right here, this is the exterior wall, this is due to heat. And over here, I've called your attention to this more than once, they did not include the bracing that was actually built into that building. So this diagram demonstrates that two beams close to column 79, D3004 and K3, had buckles in the analysis, and beam G3005 buckles in the analysis as well. So there's three of them. Okay. the diagram here demonstrates, with those braces in there, it doesn't buckle. So now you only have these two that would be buckling. The diagram demonstrates that the two beams closest to column 79 have buckled in the analysis. However, beam G3005 up here did not buckle as claimed by NIST, as there were three transverse beams, S3007, etc., that were omitted from their analysis. So I've just shown you that, okay? So more evaluation of the NIST analysis. The next 5 slides that I'm going to share with you show that the simulation of floor 13, even if the side plates were not part of column 79, girder A2001 would still not be able to travel far enough to lose its seat support. The reason is simple. It had partial height bearing stiffeners which stiffened the flanges of the girder, thus preventing it from failing. But NIST did not include them, and yet they were there. So here are the bearing stiffeners I'm talking about. This is girder A2001. Here's the base plate, and here are the bearing stiffeners. They were there. And here's our model showing them. This is the Abacus model. This is with the side plates. All that kind of stuff is there. You see, that's our simulation, a virtual simulation of the same thing that was built. That's what we did. We broke them out. This is another depiction of the NIST report showing that the bearing stiffeners were omitted. You don't see them. Another depiction from the NIST report showing the bearing stiffeners were omitted from the girder. So here's the W33 by 130 girder, column 79. Here's the W24 by 55 floor beam. And so this is A2001. Concrete slab, metal deck up here. This is the arrangement. Again, another view. This time, no side plates. Using the NIST, you can see where it still didn't drop off the base plate. It hadn't moved enough to make that happen. Yep, it was getting way too close, for sure. Another view of it. Okay. Issues that led to the 5.5 inches of movement. Non-composite main girders, neglected thermal expansion of the concrete slab, separated connection modeling, and missed web flange stiffeners. I want to point out that I think you can all imagine, I haven't talked about this yet, but if you take steel, it has a thermal expansion of about 6.5 times 10 to the minus 6 inches per inch per degree Fahrenheit. If you take concrete, it's made up of rocks, water, cement, and the kind of aggregate and the amount of aggregate is going to significantly affect that thermal expansion. Limestone, for example, has a very different thermal properties than does sandstone, than does dolomite, than does other rocks. Each one of those have thermal expansions that can be from 2 times 10 to the minus 6 all the way to 12.5 times 10 to the minus 6, depending on what you're putting together with that steel. In this case, I tried to do our best to locate what the aggregate was that they were making concrete with in that area and put that into our model, okay, to simulate what was going on. Here's the comparison of the UAF NIST modeling approach. Steps taken. The floor framing, steel connectors, springs, yes, we had them. NIST had some, but not all. Exterior steel framing connections include springs, yes, they did not. Girder to column stiffener plates, we included them, they did not. Floor beams that were composite, floors that were composite with beams, not major girders, we considered them. Floor beams that were composite with beams and girders, we considered them, they did not. Thermal expansion of the concrete deck, we considered it, they did not. And thermal conductivity and expansion of material properties, we considered it, and they did not. So, now, what about the NIST fires? This is the distribution of the heated up floor systems due to, at different times at floor 13, by the NIST temperature distribution. And we did some modeling of the temperature within the floors and came up very similar. So no arguments there, and we used these temperature distributions as part of the analysis. The UAF WTC7 Abacus modeling, this is kind of what it looked like. You can begin to see that This is for floor 12 and 13, not for all 47 stories. You can imagine what it would have meant to do that. We took a look at the connections between the deck and the beam, and I haven't put very much in this slideshow about that. But basically what we did is we looked at a frame insertion point, joint offset, and we then accounted for the interaction between these two when they were acting compositely. We then looked at sample connection response. Here's a sample connection. I'm not going to show you all of them. I'm just going to show you a snapshot of what we did. Here is the model. Here is its performance steel loading versus displacement. We ended up with a behavior that looked like that, and here's where it was located in the building. Then we took another one. This was what they call the fin connection sample, where we had an interior girder going into a beam, W16 by 26, and we modeled it, and that was what's called F, and that's where it was located. And so we took each one of these, put them together, and put it into the structure. This is the abacus connection model that I'm just talking about. You can see it's a shear connection, just bolts. It's not, the flanges are not fastened to anything to resist moment there. Here's an example of it behaving. What is it? Oh my gosh, it's actually moving, you see, and it has the bolts there, the shear bolts, and that's pretty much how it's going to look. And this is a moment rotation curve for that. Despite the fact I said there's no moment, the bolts are still resisting some twist, some rotation. Okay, here's another look at what it's going to look like if it's really starting to get stressed. Okay, shear displacement. Then what I'm going to take you to now is what we call the UAF SAP 2000 collapse computer model. This is the 47-story, floor 3 to 47 stories, including all the bracing and the framing, three-dimensionally.
The structure was built on a substation.
The structure was built on a substation down here. I didn't talk about that much. I guess I had enough to talk about for 4 years, and I didn't want to hold you that long. So we have basically computer models to look at what's going on. Oh, I'm sorry, I'm going in the wrong direction. I apologize. Remember that we saw a fairly significant amount of load that column 79 could take in if we'd had a 200 degrees C, and so 5,142 kips was what actually was acting on that structure at that day. It moved 1.92 inches to the right and 0.73 inches upward. This is a composite response. What do our UAF conclusions say? The concrete floor beam diaphragm stiffness is significant even with no shear connectors because there's friction between the concrete and the steel framing, and it's not trivial. The thermal expansion of the concrete deck cannot be ignored, and it's likely with that less than steel, the value is highly dependent on the type of aggregate. Okay. I've intentionally taken you down redundancies all night long because I wanted you to be able to remember what I was getting ready to say. The research team evaluated fire by considering the airspace below the beams and the space between the drop ceiling and the structural steel framing. I initially did not intend to do that. Our dean said, maybe you should think about that. So I did. So we did look at that issue. The result is that the fire underneath will likely burn through the drop ceiling quickly, and its resistance to heat transfer is likely not available to help anything. The NIST vertical collapse was not consistent with that of the actual observed collapse. The difference was primarily influenced by their not modeling a significant portion of the structural framing connection details. At least that was certainly some of it. So what about the actual collapse? What about this? We evaluate possible failure modes using SAP 2000. We conducted failure mechanism studies using both Abacus and SAP 2000 to ensure reliability and accuracy. What I'm saying is that we would take, there were people who would contact and say, hey, take out all the core columns, and then the exterior columns will be folded inward and they'll buckle, and that's what that's what really happened. We would try it. We would try it just to see, and we could never get that to actually show up as one of the mechanisms for failure. We did it over and over and over again. A number of engineers said it had to be that. It just would not be the case.
These included.
We evaluate collapse for various conditions. These included failure at the substation level. That's basically at floor 3. I was concerned initially when I came into this that maybe the support system at the ground level might have been the problem. Damage imposed by falling debris from towers 1 and 2. We examined that. Did it cause a problem? It really didn't do very much damage, but we did consider it. We looked at the radiant heat from towers 1 and 2 and its influence on the building structure. Not much influence. The building response for various columns being taken out, we did spend a lot of time with that. And I would have spent time with other things if it hadn't come to the point where we knew right away that there was nothing going to happen to follow that path. It just was not going to get us there. UAF methods for assessing building collapse. Here's the UAF collapse simulation velocity is a red, and actual building collapse velocity by David Chandler took the video and monitored aspects of it in time and plotted it. He was a physicist, and over a 2.5 second period, and you can see it's free fall. That's what that building did. And our red simulation points are very much on top of that, just to kind of give you an idea. So what about the collapse? We evaluate numerous progressive collapses, hypotheses, but we found it did not experience a progressive collapse, and yet we also then determined that it was going to be a global collapse. So the first global collapse simulation in perspective 1 is about what we're ready to look at. The simulation was done to compare with the collapse footage, and the collapse we're looking at right now is basically all the interior core columns were taken out at floor 13. We need 8 stories below that to provide space for that building to fall without being resisted. So floor 13, we took those out. 1.3 seconds later, we took out all the exterior columns at that floor. That's what you get about ready to see. This is the still of that. This is what's going on. What you see on the left is our simulation. What you see on the right is the building. Okay. First global collapse simulation in perspective 2. So we're going to look at it from a little bit different direction. Simulation was done to compare with the collapse footage, and this again was set at floor 13. So here it is. Okay, I'm going to do something here. I'm going to go back up to here. I want you to be aware that when we started, we noticed that NIST did this, and we did it too. So the question is, this penthouse starts coming down first, and because it's coming down first, what is causing that to happen? And we determined column 7980 was causing that to fail. Remember, we spent a lot of time at column 7980. So we then took it out at floor 13, just like other people did. And then I began to ask the question, what if we took it out up here? What if we took it out up here? What if we took it out up here? And we were not able to get the time simulation to work until we started getting higher and higher. So right here, when you watch this video, it's about floor 43. But but I took it all the way up to 45, and we were almost dead on to the actual footage of the failure. Now just let me show you what I'm talking about. Here it's going down, and notice it's going to stop right there. Okay? And that's way above any fire. The fires were all floor 13 and below. So it wasn't a fire that caused that either. Okay? So this is the second global simulation in perspective 1 that I want to show you. Here I'm not cutting them off at floor 13. I'm cutting them off at floor 19. Okay? What does that look like as an example? Here is what we're about to see, different perspective. And here it is.
Then we move back there. Whoa, 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 whoa!
Second collapse.
Okay.
Perspective 2.
Second collapse, global collapse perspective 2.
Here we're going to show you a videotape of the collapse itself. Now we go to videotape, the collapse of this building.
And then progressive collapse simulation for NIST.
And then progressive collapse simulation for NIST assumption.
We're doing was showing you
Now here's where what we were doing was showing you what we found.
what
What I'm going to do is share with you what
we're going to show you. Our
NIST said had to happen, and we're going to show you the response,
simulation was based
computer response to that, okay? The simulation was based on this assumption that column 79 buckled at floor 13, which led to the global failure of the building.
static analysis.
The progressive collapse was simulated with the help of static analysis by progressively taking away those columns that failed. So when you take out some columns out, the load's still there, it's got to be taken by something else, right? And so we progressively took them out and took them out and took them out to get a handle on what it looked like. So here's where we started
And here's what
with the whole three-dimensional building, and here's what it started to happen
so it wasn't
by taking them out.
we see. It wasn't the collapse.
So it wasn't the collapse we see, it wasn't the collapse that they showed on their computer, but this is what, if you take the story and put it into the computer models, this is what you're going to end up seeing, tilting,
was pretty confident I was going to
which is what I
start this.
was pretty confident I was going to see when, on the first day I started this and looked at that centroid issue. Because I'd done enough high-rise buildings to know that, you know,
Straight down.
they're not wanting to fail straight down unless they are uniformly
So the analysis
distributed.
was based on
Straight down.
this assumption of
Straight down.
39.
So the analysis was based on this assumption of column 79 buckling at floor 13. The static analysis started by failing columns 79, 80, and 81. And even though through the analyzed axial forces it didn't exceed their design load capacity, you're going to see green circles. What I'm getting ready to do is share with you, green circles mean it didn't exceed the capacity. Red circles means the columns exceeded their design load capacity. So here we go. There's three columns that did what?
Did not, right?
Exceeded or did not exceed?
We don't see anything.
Did not, right? So we don't see anything happening yet. Still, here is, again, nothing failed at column 79, 80, and 81 were removed, but columns 76, 77, and 80 were removed to initiate progressive collapse. We took them out anyway, all right? Here's the look at the floor system, if you look at it from a side view, and then you begin to take these out as you move forward. So some of the columns started to fail and were significantly signified by the red, and then the green circles again signified the actual load that didn't exceed the column load capacity. We keep taking them out, now there's no columns left, and there's nothing there to carry the load. And here, by more than failing 5, it can be seen that it does not match the video. So here is what the building would look like in a tip mode, and that would be another view of that failure, and so forth. Okay, so that's my story. Here's the summary and conclusion, and then I'll let you go home and eat. So WTC-7 did not fail due to fire. WTC-7 did not experience a progressive collapse. WTC-7 came down as a global failure in free fall. The penthouse failed when column 79 lost its support at near floor 45 above the fire, and this failure occurred approximately 5.5 seconds before all the inner core columns failed lower down in the building. After the interior core columns failed, 1.3 seconds later, all the exterior columns at that same floor level failed. We do know that more than one possibility could have occurred to give you almost identically the same thing. We know from floor 13 to 19 for sure we could simulate that very easily. While the failure could have occurred over 8 floors at various heights of the building, video footage showing floor 17 to 47 moving forward or downward as a unit suggests the failure occurred at or below 6 to 16th floor. That's just to put it together. Okay, so are there any questions? I apologize for taking your evening.
Thanks, Ray. Do you have any questions?
There's one back there.
So, when you showed us your chart
the total movement of that area was to the east, but the relative movement was not. Okay? Because it had to do with girder A2001 moving in one way and the column being in a different location. All right? And so it was the relative movement between those 2 points. Yes?
In one of your later slides, you showed columns with green circles and red circles.
Correct.
So the green circles are within their design specifications.
Correct.
And the red circles had exceeded their design.
Correct. So we took them out.
Engineering design, especially in structures, tend to be very conservative.
Correct.
If the design load for a particular column is X number of pounds, is that the actual failure point, or is the failure point ridiculously higher due to conservative design?
Well, keep in mind that when you design a building like this, you're designing it for dead load, which means that that's the self weight of everything there. And then you're going to be designing it for live load. That's serviceability conditions. That's the use of the building. And that's what you would size it for, and then you would size it to be ensured that you got a factor safety somewhere above 1.5, maybe even maybe 2. Okay. Okay, in this case, when that building came down, there was nobody in it. There was no live load. There was only dead load. And so, by taking out these columns, what we were doing was illustrating that if they did come out, if they did have an interruption of some kind, what would the failure mechanism look like? That's what that is about. Trying to utilize NIST assumption and see if we can make it work.
The actual load that would cause a failure is generally higher than the design load.
Absolutely. But remember that if the temperature was high enough, you're going to lose a lot of that capacity. You follow what I'm saying? Oh, we started now. I'm not going there. I can tell you what had to happen to make that, and I showed you that. Yes, go ahead.
Couldn't help but notice the discrepancy with the doing up on the left and the place.
Got a kink in it.
It's got a kink in it.
Ours did. It was just not quite as deep.
Ours did. It was just not quite as deep as what it looked like in the video. But it did have a kink. We spent 3 weeks trying to find that kink.
What would cause that kink?
And seeing what would cause that kink to occur. Because, you wouldn't have expected it to occur. But it was there. The other thing I didn't bring up to your attention, which I should, is if you look at the building, it had a surfacing on the outside and windows and all that kind of stuff. And if there was any relative movement of one column to another, all the windows would be breaking. You would see cracks and distortion in the exterior sheathing because those were non-structural. You didn't see any of that, hardly any of it. So, and even in our computer models, we were not getting very much relative movement to cause that kind of stuff to happen. So that in itself was kind of significant. If you just step back and take an overview and look at the building, it did not do this. Otherwise, you would have had breaking of glass. You would have had breaking of the exterior surfacing. And that's not structural. It's not hardly any load that's capable of transferring that. I'm sorry?
Was that why we didn't see the in the model?
I'm not sure about that. I think about that.
Yes, sir. What was the 0.0
time duration between the fire breaking out and the collapse
One and two was around 10 o'clock and
in
11 o'clock.
reference to 1 and 2 collapse?
At 5:20.
1 and 2 was around 10 o'clock and 11 o'clock in the morning. This was at 5:20 in the afternoon. I'm sorry?
Interesting.
Yeah. Yeah, 5:20 in the afternoon.
Any questions? Okay, thank you very much. Okay.
Appreciate it.
Congratulations on a great study. Hope we get good response from the nation, and look forward to more results.
Thank
Thank
you.
you all for coming. That's very nice. Congratulations.
Sound okay, huh?
Yeah. Good.
Great work.
Are all the people who, the engineers and architects, are they going to be reviewing it, you think?
They will review, but, I wanted to also be externally reviewed.
Thank you very much.
You betcha. Thank you.
Yeah, I just talked to her today. Doing well. She's going to be back here next summer.
Every now and then I see her in Facebook.
Very interesting. I can see it.